Okay, continue on here, chapter 2. So last time we talked about measurements and again, taking proper measurements. Remember that really any type of measurement, as we talked about, there's some degree of uncertainty that's going to happen. So you want to make sure that you always take a look at the actual scale that's on the piece of equipment. And really, as we talked about, there's kind of really two pieces of information that's kind of important. First off, really the ones that usually have the markings is sort of whether it's the largest markings represent. So for example, in this particular case here, that would be 10 milliliters. And then you want to also think about how many of what is sometimes referred to as the smaller markings there are between those two values. And remember that when you do count, we always count sort of past the last marking. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And there are 10 markings in this case. So really you can take 10 divided by 10, and that will tell you that each of the smallest markings represent 1 milliliter in this particular case. We talked about sort of the uncertainty of the equipment, the tolerance of the equipment. You can figure out the uncertainty in any piece of equipment you are using, usually by just taking the smallest marking and dividing by 2. So in this case, if we did that, we would end up with 0.5 milliliters. What that really tells you is not really about the 5 part of it, but it tells you really how far you can take the reading in this particular piece of equipment. And this particular piece of equipment, you could take it to the first decimal place. So again, if we did have something, say, in that region, that would be 11, 12, 13, 14, 15, 16. That would be 17. And remember that we always record when we take a measurement all the certain numbers, and those are the numbers that no matter who looks at it, everybody should agree, and everybody should agree at least is 16 in this case. Remember that when we do take a reading of a liquid, we have the curvature of the liquid, which is known as the meniscus, and we always want to read from the bottom of the meniscus. In this case, this is where the estimate is going to come into play. You know, I may look at it and go, it's kind of close to 16. Maybe it's a 4 milliliters. And we can put the uncertainty in there, plus or minus 0.5 milliliters. And remember that when we do this and we take a measurement, we always want to record, as I mentioned, all the certain numbers plus that first uncertain number, which is sometimes referred to as the estimated digit. And when you do that, that is, as we talked about last time, really, you know, the significant figures that you have. So this guy here would have 3 significant figures, with the estimated or uncertain digit being the 4. And, you know, for the most part, we sort of assume that the last digit is kind of plus or minus 1. So we're saying, you know, we think it's 16.4. But somebody else may look at it and think it's 16.5 or 16.3. So again, there's a little bit of error or estimation that has to occur in that digit. Any questions on that there? Okay. Remember as well that you want to make sure that you record your measurements always to the proper number of digits. And that includes even if you felt like, for example, we got to 18 here and it was like right on 18. In this case, we would want to record 18.0 milliliters, keeping the 0 there, which would give us 3 significant figures, with the 0 at the end there being significant. Again, if we just lop off sort of that extra 0 in this case, and we just did say 18 milliliters, that would only have 2 significant figures, where the uncertain number in this case would actually be the 8. And that means that we're saying, well, I think it's 18, but maybe it's 19 or maybe it's 17. That's a pretty big run of maybe it's somewhere in there, rather than what it really should be over here on this piece of equipment, where we're saying, I think it's 18.0, but you know, maybe it's like 18.1, maybe it's 17.9, much lower degree of error. That's why it's always important on those pieces of equipment that if you can take it to a certain digit, that you really do take it to all the digits. You really are, as we talked about last time, making your measurement pretty much crappier if you sort of lop off the digits. and making it really a worse measurement. Any questions on measurements, how to take it? We also spent some time last time talking about scientific notation and how to do it on your calculator. Remember, you do want to make things just to make sure. Again, here we do see our meniscus and something like our cylinder. Once again, if we took a look at this, we got a 10 milliliter difference with 10 markings as we go up, which means each of the smallest markings are 1 milliliter, which if we divide it by 2 means we can take it to really the first decimal place here. So looking at this, this would be 41 right here. This would be 42. This would be 43. I'm sorry, I'm counting backwards. I'm going the wrong way. This would be 30 down here. 31, 32, 33, 34, 35, 36, 37, 38, 39, and 40. That would probably be the better way of counting. And so we can see it is at least 36, which is right about here. It's not quite 37 as the bottom of the meniscus is here. So again, they estimated it at 13.8, meaning that this measurement does have 3 figures. Value really relying right there at the 8, where the uncertainty comes in. So digit or estimated digit doesn't always have to be a 5. You know, if it looks halfway between the 2 markings, you can make it a 5. If it looks closer to maybe the top marking, you can make it a 8 or a 9. You can make it a 3 or a 4 if it's closer to the bottom marking. So it doesn't necessarily have to be that. Remember that the estimated digit is not always the last number that is written, but it is the last significant figure that actually is written. And that's an important thing to keep in mind. So sometimes people think it's always going to be the last number. May not always be the last number, but definitely the last significant figure. Any questions on that one there? As I was thinking, we were looking at the wrong picture. This is a burette, which we do use in chemistry a lot. We use it for titrations. We'll use it in a few experiments down the road towards the end. But a burette's a little bit different. We actually fill it from the top, and we let it go and drip out from the bottom. So because we actually fill it from the top, a burette is a little bit different in terms of how we take readings. What you'll actually find at the very top where we fill it is actually 0. And then it actually increases in volume as you go down. That's because we fill it to the top and then we drop it out the bottom. Now, that's important because when we look at something in terms of a volume in a burette, let's just say we had some liquid between the 2 and the 3. Because it's actually increasing as you go down, if this is where our meniscus is, it's actually 2 point something here and not 3 point something. So it actually does increase as you go down. When we use a burette, there's really things that we always do. A burette's a very common piece of equipment. It's got a little, what is referred to as a stopcock down there. It's basically just a valve you open and shut. You could open it, let it drip. You could shut it to shut it off. It's a very good device to deliver a very specific volume of liquid with pretty high accuracy. When we use a burette, we usually record 2 things. We record the initial burette reading. So wherever the liquid is, we actually record the actual number. And we usually will record the final burette reading. So we usually, after we add a certain amount of liquid, we will take a final burette reading. And what that allows us to do is figure out the volume of the liquid that we added by taking the final volume minus the initial volume. So let's just say that, you know, we started here at 28 exactly, and that would be our initial. And let's take a nice even number there. We ended at 29 milliliters. So our volume of our liquid in this case would be 29 milliliters minus 28 milliliters. And in this case, we added basically 1 milliliter solution was actually added. So we always take those 2 readings when we use a burette. It always starts at 0 at the very top. So if you fill it to the very top, it's actually 0. Sometimes these commonly come in 25 milliliters or 50 milliliters in terms of their volume. So a common mistake people do is they fill it all the way to the top and go, oh, it's a 50 liter burette, it's 50 milliliters at the very top. So you always want to record exactly what the scale says. So it should always say 0, and that's what you should record. Now that I scribbled all over this, let's take a look and see the actual reading that we see here. So in this particular case, we do still have a 1 milliliter difference between the big markings. There is, again, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings, which means in each case here, each of the smallest markings is 0.1 milliliter. Once again, if you want to know how far you can take the reading, divide it by 2, and that tells you you could take it to the second decimal place, which is very common with a burette. So if we do this, remember it increases as we go down. So this is 28.1, 28.2, 28.3, 28.4, 28.5, 28.6, 28.7, 28 .8 and 28.9 right there. So it is between the two markings. So they recorded 28.8 as the certain numbers, with the last 5 being estimated digit there. And that gives us 28.85 milliliters, 4 significant figures in this particular case, with the 5 at the end being the estimated digit. Any questions on that one? So burette's a little bit different than a lot of pieces of culture that you use, because the scale is sort of backwards. And again, it's because we really do fill it from the top and let it go out from the bottom there. Okay, let's take a look. So once again, this is a burette. So we're going to fill it from the top, and it's going to, again, drip out the bottom. So if we just look at any sort of scaling of marked numbers, we have a difference of 10 milliliters. There is, again, if you count each of these dashes here, 10 dashes. So if we divide it here, each of the smallest markings represent 1 milliliter, basically 10 divided by 10. That means that in terms of the uncertainty here, if we divide that again by 2, that takes it to 0.5 milliliters, which means proper reading of this should go to the first decimal place. So here, if we look at it, this would be 11, that would be 12, that would be 13, 14, 15, 16, 17, 18, 19, 20, 21, and looks like perhaps it's right there on 22. So are certain numbers, once again, because we do have the ability to take it to the first decimal place, as we talked about last time, we do want to preserve that by putting a 0 there, and we should record 22.0 milliliters. And we could include our uncertainty there as 0.5 milliliters plus or minus. This would have how many significant figures? This would have 3 significant, certainty being right there at that 0. So it looks like number or letter D would be a winner on this one. Any questions on, again, measurements and how to take measurements here? Yeah. I'm sorry, say again. Report. Right. So here's where the liquid is right here. So that's where the liquid is, right? So it's filled from the bottom, right? So if you fill something from the bottom, as it goes in, it's going to fill from the bottom up, right? So we stopped, and that's how much liquid is sort of in there at that point, is actually at the 20, we're at the 22 marking at this point. Yeah. Most likely what happened is maybe we started at 0 and we opened it up and let it drip out the bottom. We stopped it, and the proper reading at this point would be the liquid's at 22 milliliters, if that's sort of your question. Yeah. So that's usually how you would use this piece of equipment, a burette. You fill it up to the top. You take an initial reading, like I said, 0 or wherever it may start. You open it up, let something drip down, shut it, take another reading. And what we're looking at here is just the reading part, not necessarily how much we put in there, but just the reading part of where it's sitting right now. Do you have a question? Yeah, so again, here's a little closer review here. So if we were to use this, for example, we're going to use this burette. What we would normally do is we would fill it pretty close to zero. So we'll say we're 0 line. Your particular piece of equipment is you always want to take an initial reading. So if we hit it exactly at that 0 line on this, we drained it down to on the we volume much, we sort of put in there. The actual amount that we put in, so if you take your final volume, right? So if you fill it to the very top, in this case, we would record it as 0, what the actual reading says. Even though the whole thing may be 50, we wouldn't record 50 because you will have the wrong volume. Let's just say we need to add more to whatever we're doing. We open it up again, right? And we let it drain. So let's say we let it drain to like exactly 25 right there, a second time. So for our second round, our initial reading was 20 milliliters. Our final reading would be 25 milliliters. In this point, the second part where I opened up for the second amount, what should I add? I added 25 milliliters minus 20 milliliters, right? We use this sort of piece of equipment, you always got to take 2 readings. You always got to take the difference between the 2, and it will tell you exactly how much you added. And it's a very accurate way to add a specific amount of volume to something. You just open up and shut it. But you do need to take all from the 2 times that I did it in this example, how much total volume did I add? So when I fill it up to 0 to right now where I stop, how much total volume did I add? 25, right? I first added 20 on the first shot, and then I added another 5 on the second shot. Overall, I added a total of 25 milliliters, which I could find from my original initial reading, right? And my final reading by taking the difference between those 2. It'll tell me the total amount that I added. So sometimes when you use a burette in like things like titrations, you'll add a little, shut a little, add a little, shut a little. You'll take these readings and actually add. In some cases, you're interested in how much you totally added all the way along the way. As long as you always, when you use a piece of equipment, take those 2 readings, you'll know exactly how much you actually add. Questions on that? Yeah. The purpose of this instrument is actually to very accurately add a specific volume of liquid, yeah, and know how much you added. So for example, when you do a titration where you use this equipment, you keep going, you keep adding the liquid in the burette until like the beaker turns a different color. As soon as you get it to turn a different color, you shut it off. And in most cases, you're interested in how much total volume you needed to add to make it get to that color. And you would do that by taking the difference between where you started and where you ended. But it's a very, very accurate device to add specific amount of liquid. Just like a graduated cylinder, it's a very accurate device to take a reading of how much volume you have. A beaker is a pretty shitty piece of equipment to use because beakers have really big openings, which means the meniscus is pretty spread out, which means if you ever use a beaker to measure out a volume and you mark it like at the 150 milliliter line, and you actually pour it out into a graduated cylinder, you'll be nowhere near 150 because the meniscus is so spread out, it's very hard to get a very accurate reading of how much volume that you put in there. So that's why we use things like graduated cylinders. It's a much better piece of equipment to take measurements of volume. why we use something like a burette as a very good way to distribute a specific amount of volume. On the next week's experiment, we'll use a pipette, which is another way to kind of transfer a very specific amount of volume. Other questions? Okay, questions on measurements or any of those things? All right, so let's officially talk about significant figures, how to calculate them, and calculations, what represents a significant figure. So there are certain rules for significant figures. The first rule is pretty much anything that is a non-zero is significant. Remember that when you are counting significant figures, you always start to the left. You start counting as soon as you hit the very first non-zero. So in this particular case, 1, 2, 5, and 9 are figures. Then have zeros, which oftentimes give people a pretty difficult time. The first type of zero is a leading zero, and all those are not significant. Those are all the zeros, very first significant figure. So for example here, none of these zeros here would be significant. We wouldn't start counting until we hit the 4, and the 4 and the 9 would be significant. So this number figures with the uncertain number in this case being the 9. We have zeros, they're sometimes referred to as trapped zeros or counted zeros, and those are zeros between two non-zero numbers, always significant. In this case, start counting at the 5. These zeros would count because they're trapped, and the 4 would, which means this guy would have 4 significant figures. And really the last zero, which is the one that gives people a really difficult time, is the zeros that come at the end. They're sometimes referred to as trailing zeros, and they may or may not be significant. What determines whether or not they are significant is if there is a decimal point in the number, the zeros that come at the end will be significant. It doesn't matter if the decimal point is 0 or not. As number, those zeros at the end would be significant. 600 written like this. There is no decimal point written in here, which means this 6 here is the only significant figure we have. The zeros at the end would not be significant. If I wrote the 600 like this, I would now have 3 significant figures, as this is significant. 2 zeros at the end would become significant because of the 0. That would be 3 sig figs. Question on that there. A reminder, I think earlier, but if you do write a number in scientific notation, all the numbers before the times 10 part are significant. So always before the times 10 part, all those numbers are significant, which means that you can use scientific notation to write as many significant figures as you may need. So for example, if I needed 2 significant figures instead of 3, I could write 1.3 times 10 to the 4th. Now I would have 2 significant figures instead of 3 up here. So as I might have mentioned, sometimes the only way to give an answer to the proper number of significant figures is to write it in scientific notation, because you pretty much can control how many significant figures you need. You just write as many as you need in front of the times 10 part. By the way, when we go from decimal to scientific notation and back, you should never lose significant figures. So you might remember an example. I think earlier we had something like this type of number, and we did 1, 2, 3, 4, and I kept all these guys. And that's because this number here has 5 significant figures. When I write it in scientific notation, it now has 5 significant figures. You should not lose significant figures as you go back and forth from position notation or decimal form to scientific notation. Also why in certain cases we go 1, 2, 3, 4, and 5. Gives us 5.320 times 10 to the minus 5. This number here has how many significant figures? It does have 4 starting there. 1, 2, 3. That 0 is significant because of the 0 decimal that is there. And that is why we keep the 0 there. If I wrote 5.32 times 10 to the minus 5, I would have how many significant figures? Would only have 3. So you don't want to lose anything along the way. Any questions on that there? Something like 0.00032005000 figures would this measurement have? I have no idea because I just started writing numbers, but let's say not significant, right? Because we have not hit that. So that's our very first non-zero. That's when we should be counting. But sometimes people go, wait, aren't these zeros past the decimal point? And they are, but we have not started counting our significant figures because we haven't hit the first non-zero. So there's still leading zeros at that point. That would be significant. These would be significant because they're trapped. Significant because they're trapped. Significant. What about the zero at the end? Is it significant? It is significant because way over here, we got the decimal point. So it is still significant. I have no idea how many that is. 1, 2, 3, 4, 5, 6, 7, 8, maybe 9 significant figures in that number right there. Any question on that? Now, let's say I had something written like this. How many significant figures? Which one is the estimated digit? Estimated digit or uncertain digit is? It is the 2 in this case. It is not the 0 at the end. It is the 2 because there's only 2 significant figures, which means the 2 is your estimated digit. So that's why I said earlier, a lot of times will be the very last digit that's written is the estimated digit or the uncertain digit, but is not always the last one written at the end. It is the last significant figure written. Any questions on that there? All right. Now there are some numbers that are considered exact numbers. Exact numbers are pretty much found one of two ways. Either you count them. So for example, if I had pencils sitting on the desk, I'm not going to find some magical experiment to figure out how many I have. I'm just going to simply. So that's considered an exact number. The other exact number are typically definitions. So, you know, we talked about 2 different types of units, metric units and English units. So if you have anything that's a metric to metric sort of conversion, that is an exact number. If you have an English to English equality, that is also an exact number. There are certain crossovers where you go from English to metric that are exact numbers. These are all exact numbers. 4 centimeters, 1 pound is 453.6 grams. Hopefully, you know, a foot is 12 inches. And equality, which each of these things are, right, are 2 different values on different unit scales, but they represent the same amount of something. So if I say that thing is a foot long, that's the same as saying it is 12 inches, right? It represents the same length, just on different units. To deal with exact numbers is this: when you are doing calculations that involve exact numbers, they pretty much can have as many significant figures as you like. There are an unlimited number of significant figures. So the good news about that is if you come across something in a calculation that is an exact number, we pretty much ignore it in terms of its significant figures. And that's pretty much most conversions that you come across will probably be exact numbers. The one sort of equality or conversions that we really should look at the number of significant figures is when you cross over from like an English to metric sort of conversion. You should look at the sig figs, except for these listed here, like inch and centimeters. Those are exact sort of definitions. But most of the time, if you cross over that English to metric, you should look at the sig figs in those. But if it's a straight metric to metric sort of conversion or English to English conversion, you don't have to worry about them in calculations. And again, you should probably know what's in this box, except for the 9 pencils, so you don't have to worry about that. Any questions on that? All right, so let's take a look at these here. First one would have how many significant figures? It would have 3, so these are all leading zeros. We start counting here. Significant, 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 so it would be 3 significant figures. Next number would have 4 significant figures because it is written in scientific notation, which means there does 4 significant figures. All of it is significant. sometimes people, when they do come across a number like this, will go, I'm just going to put it into like decimal form. So they move the decimal place 2 places this way and write 127. Problem with that is it has how many significant figures that one? The original number had. The proper way to do that is you kind of has to do that. Yeah. So you want to look at it in scientific notation. If it is written in scientific notation, all those numbers are significant. Don't convert it to a decimal, because a lot of times people with that. This guy here should have 3. Would have 1. Not significant. There is no decimal point actually written, even though sometimes we assume there's like 1 at the end, but it needs to be actually written in order for that 0 to be significant. And lastly, the last guy there does have 4 again, leading zeros. We would start counting here, significant, significant, this zero, significant, because of the decimal point that's there. So we would have 4 significant figures. Any question on any of those there? All right. Let's talk a little bit about rounding. Normal rounding rules apply. If the digit where you need to round, if the next number is less than 5, so 4 or less, we usually just drop off the numbers. If it is 5 or more, we round up. So if I have a number, for example, of 13,333, and I want to round to 2 sig figs, what should the answer be? 13,000, I heard. About 1.3 times 10 to the 4. About 1.30 times 10 to the 4. All right, so these are a couple of different ones that I looked at here. So let's go with second significant figure would put us here, right? So we would look at this number to decide rounding. And I obviously should drop them, right? And if I drop them, I end up with this number, which is 13. 13 has 2 significant figures. It does have 2 significant figures. If I owed you $13,333 and I said, I'm going to pay you 2 significant figures, here's $13. Am I going to make it out of the room? Probably not. Oh, hopefully you're friendly people, I'm sure. But there's a very big difference, right, in the meaning of $13 and $13,333. So if you ever want to go crazy where we change the meaning of the number, so this would not be a good way of presenting that. Here, would this be? How many significant figures the way I wrote it? It has 2, which is what we're shooting for. So 13,000, 13,333, pretty much the same value, right? We didn't really change it all that much. It has 2 significant figures, so that would be an appropriate way to do that. Perhaps you give me the $333 teacher discount, right? You know, look it over, it's okay. How about this one? Would this one be okay? How many significant figures are? There is 2. And that also is basically 13,000. So that would be okay as well if you wanted to do scientific notation. How about this one? That has 3 significant figures, which would not be okay. So it's really important when you do rounding, and sometimes it happens a lot in chemistry. People are so focused, as you should be, on giving your answer to the right number of significant figures that you to the right sig figs, and you really change the meaning of the number. You do want to do proper rounding, but you never want to change the actual sort of meaning of the value. So just keep that in mind as you do it. Also, in terms of rounding, it usually is a good idea not to round too much if you're doing a lot of calculations in a row. Like if you're doing a calculation, you get an answer, you take that answer, do another calculation, get an answer, kind of keep doing an answer and using it. Usually hold off rounding to the very end. So if you're using your calculator, leave all the numbers, kind of keep going, and then kind of round off at the end. You do keep track of everything and sort of clean it up at the end to the proper number of sig figs, which we're going to talk about here in just a second. But a lot of times, if you round a lot after you say get the first answer and then get another answer and round a lot, every time you round, you're farther and farther away from the correct answer. So you usually want to just keep track of everything, kind of really clean it up and round everything at the end along the way. Sometimes people will keep track of things like going, okay, well, this is kind of like where I should, kind of stop and just keep track of it, but use a few more numbers in your calculations. Any questions on that there? All right, so if we're going 2 sig figs, first one should be rounded to what number? It should be 36. 2 sig figs is here. We look at this, which is a 7, so we want to round up, which would take us to 36 meters. 2 sig figs on the next one would take us to the 8. We would look here, which means we're not going to round up. We're going to drop the numbers. But in this case, I do need to write the zeros. Why do I need to write the zeros? And I probably, I need to write the zeros because of the same thing we just talked about. If I could get rid of the zeros and wrote 38, that's a very big difference, right? 3,800 versus 38. So we need the zeros to keep really the meaning of the number. Another way I could write this is 3.8 times 10 to the 3, right? 2 sig figs, 2 sig figs. If I put a decimal point at the end here, is that okay? It would not be okay because then I would have 4 significant figures, right? So again, we want to keep track of that. Any question on those first two? Next one, our second significant figure, we start counting here, brings us to here. We're going to look at this number. Once again, here, we're going to drop. Did I drop the zeros? If I kept zeros in that, how many significant figures would I have? I would have 4, which would be too many for what I'm shooting. So in this particular case, we actually need to drop it. It doesn't mean because it's a small number. So sometimes you might need to drop them all together. Sometimes you may need to convert those last numbers into zeros and keep them to make sure that the magnitude of the number doesn't change. Lastly here, that's going to give us a 1.3 kilograms. Any questions on any of those there? So more important, let's talk a little bit about how we deal with significant figures and calculations. There's really sort of a few things that we do. We oftentimes will either multiply or divide. When you multiply or divide, your answer should have the same number of significant figures as whichever number had the least number of significant figures. So if you're multiplying a bunch of numbers together, the one with the least number of significant figures should be how many significant figures your answer has. So if we took 4,437 times it by 3.20 times it by 1.2222, this has 4 significant figures. This has 3 significant figures, as that 0 is significant because of the decimal point. Answer should end up with 3 significant figures when we do that. And in this case, it looks like, I hate this calculator, but I'll give it a try. Not understanding where the decimal. I think this is 17353.28448. Reminder, your calculator doesn't give you the right number of sig figs, right? So going with this, we want 3 sig figs, which takes us here. We need to then round up because of the 5. We also need to keep the zeros to maintain the value of the number. So we should end up with 17400 as our answer in this particular case. Any questions on that? When we add and subtract, we actually do something a little bit different. When we add and subtract, we're actually looking at decimal places, not significant figures. So we're looking at the one with the least number of decimal places is how many decimal places your answer should have. So if we were adding something like 4.255 plus 1.30 plus 1.111. I'll try without the calculator, give it the old college try. Oh, it's a lot of sixes. Look at that. All right. So 4 or 5. Oh, it's a bunch of sixes. All right. Well, there you go. All right. So in this case, we're going to look at decimal places. This guy has 3 decimal places. This guy has 2 decimal places. And this one has 3 decimal places. So we actually would take this to 2 decimal places. In this case, we then would need to round up, and we should end up with 6.67, which has 2 decimal places. How many significant figures does it have? It has 3 significant figures, which would be important if maybe you continued on and took and did some type of other calculation with it. Any questions? So multiplying, dividing, you look at sig figs least number. Adding, subtracting, look at decimal places, also the least number. Reason for that is your least number is pretty much your worst measurement. So your overall calculation is only as good as your worst measurement. Kind of like the weakest link, right? You're always good as your weakest link. So your worst measurement is as good as your calculation would be. Question on that. Now what happens, I did a little combo action here. I did something like 32.5 by 435. When we do math like this, we typically would do which part first? The part in the parentheses we're multiplying, which means we're looking at significant figures. This has 3 significant figures. This has 2 significant figures, which means when we are done with the top part, we should really have an answer that has 2 significant figures. We then would be taking a number with 2 significant figures and dividing it by a number that has 3 significant figures, which means my answer at the end should have 2 significant figures. So would I round personally? I probably wouldn't. I would keep track of it. So, I would do 32.5 times 1.2. And that ends up actually at 39 up on top. We then would divide it by 435. And we would end up on our calculator 0.089655172. Here again, 2 sig figs, 3 sig figs, 2 sig figs would take me to here. What should I round that to? 0.090, right? Because we do need 2 sig figs. Without having that 0 there, obviously we would only have 1 sig fig. You could also do scientific notation. 9.0 times 10 to the minus 2, 1 and 2 to do that as well. Question on that. So let's say we did 4455 times 12 divided by 1325, and then let's just add it to 1.77. I will do it as well because, again, I just made it up. So let's see. Okay, let's take a look. So again, here we would probably do, obviously, the part in parentheses first. So that is a 4455 times 12. And that does give us an answer of 53460. Technically speaking, how many significant figures should that number have? Should have 2, as this has 4 and this has 2, which means really we should end right about there. Now, sometimes people will put the little line up on top to sort of keep track of it. Personally, if I was doing this, I would keep the whole number in my calculator and then divide it by the bottom number. So that's what I'm going to do. If you don't want to do that, you probably should keep a couple of digits. They sometimes refer to as guard digits there, so you don't round too much, or just keep the whole number. I'm going to divide it by 1325. And that's going to give me a number of, I believe it is 40.3471691. Now, technically speaking, my guy up on top should have 2 sig figs. My guy on the bottom has 4 sig figs, which means technically speaking, this answer should, which takes us to here, which means technically speaking, we should drop all that, which means we're now going to take 40 plus 1.77, which gives us 41.77. The last thing I just did was adding, right? What should I take? This guy has how many decimal places? There's nothing right there, right? This one has 2. So we would actually take this to a whole number, but because it's a 7, it should end up at 42. Questions on that? So what you should do is, as I mentioned, you should really avoid rounding to sort of the very end, but you should sort of keep track of everything along the way. And sometimes you may be mixing, adding, subtracting, multiplying, dividing. Again, if you just avoid that rounding to the end, you'll be in good shape. If you do a lot of rounding, you're gonna be kind of far away from the right answer. Any questions on calculations? Yeah. You could as well, and I think in this case, you'll get a similar answers. Yeah, so if you didn't want to round it, I mean, at this point, you could round since you did a lot of the calculation, but if you kept it, it would be okay as well. And in most cases, I probably would have just continued on with my calculator and then added the 1.77 to it. Other questions? But as long as you don't kind of round up to the first step, second step, you know, you should be okay. All right, so obviously when you do calculations, you want to make sure that you always end up to the right number of significant figures. So if we do this on our calculator, remember our calculator doesn't always give it to us in the right sig figs. This guy should round to how many, or where should we round this guy? This guy, we're multiplying, so we're looking at sig figs. So this is 3 significant figures. This is 2, which means we should end up here. And this should round to 9.4. Yes. So this guy should round to 9.4. What should the next one round to? Not everybody at once. What should the next one round to? Yeah. How many sig figs decimal places should I have? Sig figs are decimal. Let's start with that. Are we looking at sig figs or decimals here? We are. So this guy has 4 sig figs, right? This one has 3, which means our answer should have 3 sig figs, which is that guy right there. That's less than 4. It's less than 0 or 1. So we will just drop those numbers, right? And that will give us our proper number. Here we are adding, so we should look at sig figs or decimal places. Decimal places, that's 2, that's 1, that's 3, that's 3. So it looks like we should end up to, actually that's the answer. So we should actually end up to 1 decimal place, which takes us to there. So we should end up at 29.1 in this case. And lastly, we're subtracting. So we'll look at decimal places, 4 decimal places, 1 decimal place. Actually should come here because that's an 8. This should round to 0.6. Yeah. Question on calculations involving significant figures. So you are expected, obviously, to give all your answers to the proper number of sig figs, and also should have units. Any questions? All right, what we're going to do next is actually we're going to skip ahead to density, as that will relate to the lab you're doing today. We will come back and do the rest of it. So density is the mass to volume of an object. We compare the density, it lets us know whether or not something will sort of sink or float. So something is more dense than water, it will sink or float. Something is more dense, it will sink. Yeah. Something is less dense than water, it will float. Yeah. So for example, if I take regular Coke can, I throw it into a sink of water. Will they both sink? Will they both float? Will one sink, one float? The answer is one will sink and one will float. Which one will float? The Diet Coke, yeah? Regular Coke has what in it? Some more nuts, yes. Good party trick in case you need, yeah? So Diet Coke will float and regular Coke will sink. So there is a formula to calculate density. Density is mass per volume. Typically speaking, they're typically associated with remember that 1 milliliter is the same as a cubic centimeter. Now you do need to know this formula. So density is mass divided by volume. Volume would be mass divided by density. Multiply volume to the other side, divide the density. And mass would equal volume times the density. Sometimes people like the DMV triangle. Everybody loves the DMV. So density is mass over volume. Volume is mass over density. And mass is density times volume. Although we won't do a lot of calculation of density of gases, but it's usually given in grams per liter. If you take 1A, you'll do some density calculations involving gases. But for us in this class, for the most part, these are really the common units that we'll see for density. Now, the number always stays with the grams, and it's always 1 milliliter or 1 cubic centimeter. So the number always stays with the grams part. There's a couple of different ways that we could get the volume. We could get the volume by simply filling something up like a graduated cylinder and just taking a reading. You could also get the volume by, like you did in lab last time, and you'll do today. You could take the length times the width times the height or the thickness. And if you measure each of those things to say centimeters, and you multiply them together, you get a cubic centimeter, which is a volume, right? So that's another very common way that we can get the volume of an object. Any questions on there? Okay, so let's take a look at one here. We want to calculate the density of a block that has 25.3 cubic centimeters and has a mass of 21.7 grams. So let's take a look at this. So obviously we have a volume that is 25.3 cubic centimeters. We have a mass that is 21.7 grams. And we're looking for density, which is mass divided by volume. In this particular case, we're good to go. We have all the numbers that we need. We just need to plug it in. So the mass here would be 21.7 grams. Divided by the volume, 25.3 cubic centimeters. When I divide that out, we get 21.7 divided by 25.3. And on our calculator here, we got 0.857, 707509. Do these units cancel each other? They do not, so they stay. So the units here would be grams per cubic centimeter. Would that be the proper way to report the answer here? It would not. So we are dividing, right? So we're looking at sig figs or decimal places. Sig figs. So top number has how many sig figs? 3. Bottom number has? Answer should have, which would take us right here, right? Looking at this number, I should round up. So the proper answer should be 0.858 grams per cubic centimeter. Again, the number does stay with the grams, and it is basically 1 milliliter or cubic centimeter. Question on that there. By the way, if you had liquids of different densities and you put it in like a graduated cylinder, they would separate out, yes, into different layers. The more dense layer would be top or bottom? It would be bottom, right? More dense. Top layer would be less dense. And if I threw something in there and it stopped right about there, like a solid thing, that means that that guy is more dense than everybody above, right? But it is less dense than everybody below, right? That's why it sits there and then it sinks to the bottom. Any questions on that? So as I mentioned, there's really a few different ways to get the volume. The two that we just talked about, just simply taking a volume reading, measuring with a ruler, length, width, height, or thickness. Now, a third way and a very common way to measure the volume, especially density, is what is known as volume by displacement. And volume by displacement means you take something, say like a graduated cylinder, like you'll do today, you fill it up with some, say, water, and you take something that is solid and you toss it in there. When you toss that solid in, what happens to the volume? Does it go up or down, or stay the same? Volume goes up, right? To a final volume. Now, this solid object will displace a volume that's equal to its own volume. So if you take the difference between where it started, kind of like what we were talking about with the burette, and where it ended, you could actually figure out the volume of the object. So in this case, the volume of the object would be our final volume minus our initial volume. So that is a very, very common way that volume is found. And like you'll do today, you basically fill up a graduated cylinder with some water, toss a stopper in there, take a reading, you'll be able to. Question. So here's an example of it. Goes for a swim. That's the initial volume. In she goes. This would be our final volume. And again, the difference between the water and the tank would represent her volume, right? Hopefully this is not just markings, but also a ladder, or she's got to hold her breath for a very long time. So a student fills a graduated cylinder up to 25 milliliters with a liquid, then puts a solid in it. It goes to 33.9 milliliters. Mass is 63.5. What is the density? Take a minute or two, see what you come up with here. This we're describing, we basically have a graduated cylinder that has 25 milliliters of liquid. She then takes a solid and dumps it in there. The volume then rises to 33.9 milliliters with the solid in there. So obviously we're looking for density, which is mass per volume, and we have the mass given to us. So we do need to find the volume of the object by taking the difference between the two, final minus initial. In this case, that would be 33.9 milliliters minus 25 milliliters. That is going to give you 8.9, I believe. 8.9 milliliters. So that would be the volume that we need. At this point, we now have everything that we need. So the density here would be our mass, 63.5 grams, divided by 8.9 milliliters. And we end up with 7.1348311461 grams per milliliter. Answer should end up at, the final thing we did was divide, right? And we took 3 significant figures divided by 2, which means our answer should end up at 2 significant figures. So we should end up at 7.1 grams per milliliter in this case. That is really based off of the subtraction that we did here. When we subtracted 1 decimal place, 1 decimal place, 1 decimal place, but has 2 significant figures, which is important when we do our final calculation step, which is dividing. Question on that there. Take a one look at this. Here's some density of some common things, but water is one that you should know. In all, if you ever need the density of water, that's the liquid, by the way. It is 1 gram per milliliter. I will tell you that density does change with temperature. So density, as the temperature changes, so does the density. There's an unusual substance because solid water, which is ice, is actually less dense than liquid water, right? When we put ice in our cup, the ice cubes end up at the top, right? And that's because when ice goes into the solid state, it creates a lot of empty spaces between the water molecules. And what that does is it actually makes the volume of ice larger. And that's important because if the volume of ice is larger, that number is going to be bigger, which means the density will be smaller. So if you ever come across a problem, you need density of water, 1 gram per milliliter is typically what it uses, but in reality, it does really change with temperature. But any book problem or stuff like that, most cases, 1 gram per milliliter is something you should know is the density of water. Any questions on any of that?